Hello, I would like to tell you about my research and how that is related to kitchen appliances, transport pipelines, and bacteria. The work that I'll be telling you about in this video is the article in the Chemical Engineering Journal called Growth Mechanisms for Composite Founding the Impact of Substrates on Detachment Mechanisms, and it's a collaboration between the departments in the Technical University of Denmark, the Department of Chemical Engineering, and the Danish Offshore Technology Center. It's Benaya and Philip Fosbol that has helped make this possible, and my name is Isaac Appelqvist, and I'm currently doing a PhD in the topic of scaling formation. So how are these three items related to fouling? Well, fouling is the formation of materials from one phase boundary to another phase boundary. That means either from a gas or a liquid onto a solid surface. And in kitchen appliances, in an L kettle, it happens when you try to heat water and you transfer heat from the steel surface to the water, and on the inside lime scale can form. And this lime scale that forms on the inside of your L kettle will lower the heat transfer efficiency, and you'll have to use more energy to heat up the same amount of water. Biofilm, or that comes from bacteria, that's also another type of fouling, and that occurs when a lot of bacteria form in the same area and then can lead to corrosion. And corrosion in pipes can give a cut through the pipe, and then can spill out what is on the inside, and that can lead to a lot of hazards for the environment. In transport pipelines, which this is a piece of, then formation of material on the inside of this diameter will lower the radius, increase the pressure drop, and you will have to use more energy to transfer the same amount of liquid through. So you see there's a lot of examples where you have to use a lot more energy to do the same things. And how can we mitigate this? Well, that is what my research is about. I'm trying to understand the fundamentals of fouling formation and thereby try to develop prediction models and mitigation strategies so we don't have to use so much energy on things that we don't want to. In kitchen appliances, we have lime scale that forms this chalk, and that is calcium carbonate. And a calcium carbonate molecule looks more or less like this. And in the kitchen appliance, that's the only thing that's forming. But in many industrial applications, it's much more complicated than just one scaling agent that forms. And in transport pipelines, which I told you about before, then barium sulfate is also a very relevant molecule. And the interaction between calcium carbonate and barium sulfate is not well understood, and that is what our work, Growth Mechanisms of Composite Fouling, is trying to understand a little bit better. So to do that, we grew calcium carbonate inside a small steel cylinder. We used it as a model reactor for understanding this growth behavior. And first we grow barium sulfate in one of them and calcium carbonate in another. And then we grew calcium carbonate on top of the already precipitated barium sulfate, and barium sulfate on top of the already precipitated calcium carbonate, as you see here on the video. And what we originally thought would happen would just be that they formed in these layers on top of each other, and maybe interacting a little bit, but what we actually found out from our experimental observations was much more interesting than just that. So when I present to you here is how much mass is forming from the experiment for calcium carbonate on top of either steel or barium sulfate. The brown one is calcium carbonate on top of barium sulfate, and you see that almost double the amount of calcium carbonate has formed. So barium sulfate, it acts as this kind of favorable template for enhancing the growth of calcium carbonate. While on the other hand, barium sulfate acts completely different as a template for calcium carbonate growth. So what we see is when we grow barium sulfate on top of calcium carbonate, it actually loses mass. So to try to understand and explain that, I will have to take use of some Lego. So if we have some barium sulfate ions that are coming to the surface and they form like a small cluster like this, then originally they would just grow in a cluster on the surface. And then afterwards, when we try to grow calcium carbonate on top of it, it would form mostly on top, as you see from this experiment, that acts as this favorable template. And what we know from the literature is that barium sulfate is a very strong and resilient scaling agent and it's difficult to remove from the surface. So it creates a very strong attachment to the surface and also a strong attachment to the calcium carbonate, and therefore it will stick like this. And from the CT scans we did, we could see that the height of these islands, they were very high and focused in the middle, so it would look more or less like this Lego build I've had here, that most of the mass was focused in the middle. On the other hand, if we were growing calcium carbonate first, so we make a small cluster of the calcium carbonate on the surface, and then we grow some barium sulfate on top of it. Then from the literature we also know that calcium carbonate is more or less like a little bit more porous material. So the calcium carbonate steel interaction, or the internal interaction inside the calcium carbonate, is maybe not that strong, and therefore it's likely that when barium sulfate attaches on top of it, this interaction here will not be that strong, and it's likely to just break off as a whole and detach from the surface. And therefore we see that less mass is forming, because when barium sulfate grows on top, it actually takes some calcium carbonate with it. And that's also in line with our experimental observations, namely that from the CT scans we saw that the left behind calcium carbonate islands, they were not as tall, but they were like flat growth. So they were more wide than tall. And this is also in line with our observations of how tall and the cluster size distribution, namely that for the calcium carbonate on top of barium sulfate, we saw that we have not so many big islands, but for the barium sulfate on top of calcium carbonate, we have islands that have a bigger lateral size. And these findings we try to summarize in growth mechanisms, which we have recently published in the Journal of Chemical Engineering. If you're interested in hearing more, please reach out to us either by finding the article link in the video description, scan this QR code for our email, write to us here, and we can have a chat about these results. Thank you for watching and have a nice day.